Hello, hello everyone. Welcome to the LIUniverse. I'm Dr. Charles Liu, your host, and of course, I would be really happy if you would call me Chuck. This is a great episode today because we are answering your questions exclusively. It's always fun. After today's joyfully cool cosmic thing, we're going to go right to your questions, and I can't imagine two cooler people that I would be loving to answer and ask questions with than our two folks here. Let us begin with our co-host, Alan Liu. Hey, Alan.
Hey,
Hey, answered any cool cosmic questions lately?
I mean, I've been in the comments answering some on YouTube every so often. I don't know when's the most recent one I did, but you'll see. I usually will sign them there if you are
Oh, that's
on our
always
social
good.
platforms.
Terrific. I'm so glad that you're doing that. Thank you so much. And someone who is normally behind the scenes on the LIUniverse podcast, but actually is right in your face, and we love it that way. Stacy Severin, our social media guru. Hello, Stacy.
Hi, guys. Happy to be
Hey.
here.
Oh, really glad. Done any cool cosmic music production lately?
Hmm. Well, for our listeners, I was actually in Chuck and Ellen's neighborhood last night playing with the Connecticut Symphonic Winds, a little bit of piccolo. So that was
Woohoo!
fun. And they were in the audience. So we had
Yeah.
That's very cool.
a little lunatics on the road there. It's great.
No, it's wonderful. You sounded great too. Do I remember that your piccolo is relatively new?
It is, yes.
And a
The other
nice.
one was suffering from metal fatigue.
That's a problem in like spacecraft too.
Yeah,
All the
yeah.
time.
Well, it was played for so many years and so much that it was time for a new one. So,
Awesome.
Wow. So
yeah,
it is now retired and is some sort of hall of fame of piccolos, right?
absolutely.
All
Love that.
right.
Wonderful. Well, let us go to today's joyfully cool cosmic thing. What is the joyful cosmic cool thing of the day? Well, it has to do with the Euclid mission. Now, those of you in the audience who are sharp eyed and sharp eared may remember that we had an episode with Dr. Yun Wang on here on the LIUniverse. And she not only is a published poet of significant substance, she also was one of the lead scientists on the Euclid mission, which is a space telescope project led primarily by the European Space Agency, but also with support from NASA and other astronomers from all over the world, that was going to take significant data about millions and millions of galaxies and other deep space objects that would help us map or start to map dark matter and dark energy as it is distributed, or if it even exists, in our universe. And just recently, Euclid has released more cool images, including one especially cool one around something called Abell 2390. Now, Alan, have you ever heard of the Abell cluster catalog?
I have heard of the catalog. I'm not sure I've heard the specific one in it.
hmm George Abell, all right, was a scientist from the mid 20th century who first did the painstaking work of putting together a comprehensive catalog of clusters of galaxies. So these aren't just,
Yeah.
star clusters in galaxies, but actually clusters of galaxies spread out all over. And he did it painstakingly by putting his eye up to a loop up on the original Palomar Sky Survey and just went across the sky and just mapped
So
thousands of
so
them.
they would take like a photograph on film of like a big piece of the sky, and then he would just like get up real close to it.
Yes, and just try to find, oh, here's one that looks like it has at least a few galaxies in it. And then you look closer and go, wow, not only are there a few big galaxies, there are a whole bunch of little ones. And so these are cluster maps. And although a small portion of them happen to turn out to be chance superpositions of nearby galaxies or galaxies at different distances, most of them were indeed clusters. And these clusters are extremely important because they are the centers, the gathering places of much of the dark matter in the universe.
Mm-hmm.
And by measuring the motions and the positions and the locations and so forth of those galaxies in the clusters, it really helps us understand where dark matter is. Now, Stacy, uh, do you have a favorite Abell cluster, or do you have a favorite cluster of galaxies in general that we can?
Ooh, clusters of galaxies is tough. I mean, stars, I've looked at lots of stars, but not lots of galaxies.
Yeah,
Yeah, there's not too many you can easily see just with your eyeballs.
that's
Yeah,
right.
I mean,
Yep.
Messier objects, I'm all about that. But I really haven't seen clusters of galaxies, at least
Right.
knowingly.
Well, it turns out that we live really close to one cluster of galaxies called the Virgo cluster of galaxies, and that's because it is in the direction of the constellation Virgo. It's only about 100 million light years away from
Oh
us.
yeah,
In fact, less than 100 million light years away from
that's
us,
only like
which is
1%
really
of the way across the universe.
that's right. It's not that far at all. It's just very tiny. And then there's another cluster, which is probably the most massive cluster near us, and it's called the Coma Berenices cluster, or Coma Cluster for short. There's a constellation called Coma Berenices, which is Bernice's hair, but
Specific,
uh, yeah, it's not a major, well-known constellation like Virgo as one of
the
the
zodiac
constellations of the
constellation. Yeah,
zodiac, right? But the Coma cluster is very interesting because it's only a few times further away from us than Virgo, but it has so many galaxies and so much dark matter, and it's a great laboratory for us to study. When you go further out, uh, at about 2 to 3 billion light years away. You get some really big clusters of galaxies, also. Probably the best known one, or one of the best known ones, that also has Hubble Space Telescope images was Abell 2390, the 2390th cluster
yeah.
of
I know
galaxies
you're the
in the Abell
guy, and when it comes to
survey.
your research,
Right,
so I know you're
right,
really into all these
right.
cool things.
Yeah, yeah, it's really cool. So, um, in this image of Abell 2390, conducted and obtained using the Euclid Space Telescope, right? More than 50,000 galaxies are visible. More than
50,000
50,000.
galaxies
Yeah,
in like the
and
one
just within
picture.
this cluster, one picture, one cluster, it's about 2.7 billion light years away from Earth. But in here are loops of gravitational lenses. There are things that are galaxies being torn apart and put back together, little groups, subgroups, gigantic groups. It's a wonderful laboratory for examining dark matter and just a super cool picture. So I want everybody to go and take a look. Okay, Euclid's latest picture of Abell 2390, because that is today's joyfully cool
It's pretty
cosmic
awesome.
thing.
Yeah, and Euclid, like, it's got a wider field of view than something like the Hubble or the JWST, which is why I can see all these galaxies at once.
Yes, that's really true. Um, there's going to be another space telescope launched in about a decade that NASA will be the lead on,
Yeah,
that will sort of follow up on the things that Euclid is doing, because it will be also designed to take wide field pictures of the whole sky. And that's the Nancy Grace Roman Space Telescope.
yeah, that one's gonna
We're
be
going to do
exciting.
some stuff about Nancy Grace Roman in future, because she is super cool. I mean, often called the mother of Hubble,
Yeah.
and just a great scientist and a great person that we all really appreciate, look up to in the telescope making game. All right.
Awesome.
So with that, Stacy, please let us start answering these questions, and we have prioritized our Patreons, who have helped make this podcast possible. And we really thank all of you who have questions, who want to let us know. As you know, we usually prioritize students, so we have a good mixture of them, as well as our Patreons and other people who participate with us through our social media channels, of which Stacy is our guru. So thank you all very much for doing all of this. Stacy, go for it. Tell us, who is our first question, and what is this question thing?
Excellent. Well, this is from Emil Roman on
Okay.
Patreon, and
Woohoo!
he's got a multi-part question,
Well,
guys.
that's
So
exciting.
let's start with the beginning. It's a real good one. He says, "Hi, Chuck and Alan. What an awesome segment name. He likes the Chuck GPT, guys."
Nice.
Good. Well, we like it too. Great to see.
Okay, now here's the nitty gritty of it all. Emil wonders what would happen if you tied one end of a really, really long rope to the International Space Station and have the other end hang down all the way down into Earth's atmosphere.
Hmm.
Ooh.
Would the current speed of the ISS circling the globe counteract the fact that the rope is in the atmosphere and experiencing drag? And would people on airplanes be able to see a rope swing by?
Yeah, this is a really cool question because it sounds like an absolutely crazy idea, and it kind of is, but also it's a crazy idea that people have come up with and actually come up with cool uses for in the past. Um,
Wow.
so this is sort of like the idea of something called a space tether, which is basically any really long rope-like object, like a cable, that you want to have in space. And there's a few different ways you can use them. One is you can use it between like two satellites that are both in orbit, where it can use to help like stabilize the directions of satellites and things. They've done some tests with that. But the other one that this one is more reminiscent of is something called a sky hook,
Oh,
which is it's sort of related to the idea of a space elevator. If you've ever heard of that, that's sort of one of these popular ideas of how you could get something into space without having to use a rocket. You just basically have a really long elevator cable from space all the way connected to the ground. The skyhook
wow.
is more like what this one is, where it's hanging in the atmosphere instead of on the ground. And the advantage is sort of you can have a shorter cable because you can go from a lower orbit. So the ISS, I should back up and talk about orbits a little bit. So
Okay.
yeah, I know I just really love this idea, so I'm
Look,
really,
there's
really
lots
into
of
it.
stuff going on here. You know, when you say skyhook, I immediately think of Kareem Abdul-Jabbar. And the
Fair.
skyhook, which was an indefensible shot,
Yeah.
right?
Well,
But so this is a little bit cool.
this would be
Also, we'll
yeah.
add this to Kareem's sort of story.
It's so cool that Alan is giddy over it.
Yeah, it's really awesome.
And that makes me excited.
Thanks. Yeah, no, a skyhook it would be an impressive basketball shot as well. So the idea is that when you have something in orbit, it's falling around the planet, and it's got a certain amount of energy and a certain amount of speed that it can use to sort of stay up there, and that's what the ISS does. And it is actually slowed down a little bit by the atmosphere.
Mhm.
So to get something up into space, into orbit specifically, you need a whole lot of energy. And the idea with the skyhook is you can sort of have something in orbit around the Earth, and it would like reach down with this giant cable, like you're talking about, into the atmosphere, sort of grab a plane from the atmosphere and like lift it up into space. And
Wow.
the idea of this is that there's certain kinds of rockets, things like ion thrusters, like the Vasimir engine that we talked about with the
Franklin Chang
Franklin
Diaz.
and Chang Diaz and
Yeah,
Miranda
right.
Chang Diaz, yeah, with the two of them on the podcast before. There's these engines that work more efficiently in space than on Earth, like by a lot. And so the idea is you could put that energy into the system up in space and then use it to grab something flying along in a plane on Earth or in the atmosphere, and then bring it to space with a whole lot less energy consumed. And it wouldn't
Amazing.
need to be as complex as a space elevator because it doesn't need to deal with going all the way down to the ground and going all the way up to a higher orbit that a space elevator would need. It's honestly, it's a really cool sci-fi idea right now. I don't think we have the ability to make it happen yet, but it was,
But
yeah.
but that would mean that people in airplanes would be able to see a rope swing by. In fact, they would feel the rope grabbing them as they are lifted into orbit.
Yeah, so for the International Space Station experiencing drag here and sort of counteracting that from the rope, it would for a while. The International Space Station has a lot of speed and a lot of momentum, and even like the very thin part of the atmosphere that's up where it is 300 or 400 miles up in the sky, that part of the atmosphere actually does drain on the ISS's energy right now. So every time a supply ship comes up, they usually boost it back up a little bit to counteract that drag. So drag is getting into the system already, and this would definitely make it a lot worse if you had something trailing through the atmosphere.
Okay,
It
unless
would be a drag.
It would be a
it
drag.
would be a drag.
The second part of the question is, would the end of the rope on the International Space Station be stretched out or loose? And would it drag the space station down in its orbit?
Yeah, so that's those are two actually really closely related questions in there. So it would definitely drag the ISS, the International Space Station, down in its orbit, just because you're losing energy to the atmosphere, just the way like when something's like a space shuttle or a space capsule is re-entering the atmosphere, it's intentionally losing that energy so it can slow down enough to hit the ground safely. So anytime you're losing that energy, there's going to be some drag, and that's got to come from somewhere. It's a conservation of energy issue, right? And so that would come from making that space station, or either the International Space Station or whatever you're connected to on the space end of it, would come down into a lower orbit. And sort of related to that, that would mean the rope would actually be stretched pretty taut, because the only way that energy transfer happens is through a force. This is, Newton physics, right? That force pulling on the space station over a distance is what's causing that loss of energy.
So it wouldn't be flapping in the breeze, so to speak.
Yeah, I mean, there'd be a whole lot of engineering challenges you could do. And so when people have designed these hypothetical skyhooks, the idea is that most of the time it's sort of like parallel to the atmosphere, so parallel to the ground, so that's not going to be dragged on as much, and it only dips down in to grab a plane or whatever when it needs to grab something. And then it does that one dip, comes back up, and then boosts itself back up in space again with those efficient engines. It's a really cool idea. I don't know if we're going to have one anytime soon, but...
Well, can I tell you that in the 1990s, I actually observed with my own eyes a tether hanging from the space shuttle.
Yeah, that sounds really cool.
This was really cool. About the time I was sort of ending my graduate school years, I was at Peak National Observatory using the Steward Observatory 2.3 meter reflecting telescope to gather data for my dissertation.
Okay.
And it turned out that very week, the space shuttle was in orbit, and they were running an experiment where they were letting a tether roll off the backside of this amazing experiment just to see what tethers would do. And it went off, it looked really cool, and then it broke. And it came down, and so this was not stretched taut anymore, but it started sort of falling through the sky. And we were able to see it just for a brief period of time when the sun at an oblique angle was able to strike it, and it reflected off. It looked like a piece of string or cotton candy just slowly wafting its way down the sky, even though it was at least 100 miles up. It was so cool and so neat. And it sort of burned up in space, so it was harmless to us down here. But that was really fun. The experiment only partially worked because it broke off. But nevertheless, just seeing it that one time, I still remember. And I was thinking about like the dragon riders of Pern.
Oh, awesome.
And the threads coming down and the dragons having to, burn them up before they hit the ground and stuff.
That's incredible.
Anyone ever read the Anne McCaffrey science fiction series? You guys got to check that out at some point.
That sounds amazing.
It was super, super neat.
Yeah.
If there's a picture of it, let's put it in the description of the video.
Yeah, we can,
a link or
flash
something.
An image up, because the
that'd be
images
great.
are nice in public domain.
Yeah, that's great. Yeah, so we'll have a link to this and other cool image pictures and so forth on places like YouTube and Podbean, where we have the podcast, so all of you guys can take a look at all these cool things that we're like talking about if you're now enjoying this podcast, just audio.
Yeah, this is I was just looking this up when you mentioned it. The Tethered Satellite System was what it was called.
Wow.
And they actually flew this on the space shuttle like you were talking about. It was not long enough to dip down into the atmosphere. It was about as long as like a football field or something. Actually,
it was ghostly.
A little bit longer than a football field, supposedly. 256 meters or 840 feet.
A long piece of rope.
Yeah,
so really long piece of rope to put in space.
2.5 football fields.
Yeah.
That's a lot.
The most proper unit of measurement for not the SI.
All right, thank you. Wow, great question. Thank you so much, Emil. This is awesome. And thank you for your Patreon support. Always appreciate that from everybody out there.
Yeah.
All right. Not another question for us, Stacy. What's next?
Okay, we have another student question here from Michael Lesnikowski.
Okay.
And I know you're going to like this one, Chuck. Is the multiverse theory true?
Ooh, is the multiverse theory true? Well, first of all, let's be a little bit clear on what the multiverse theory is. And then we can say whether it's true or not. Okay. Now, the multiverse theory in general just means that there are lots of different kinds of universes that all happen to exist at the same time or in the same space. And we just there could be someone doing this very podcast, you and I, the three of us doing this, but me, instead of wearing the shirt that I'm wearing now, which is, a really cool blue and white shirt for those of you who can't see, maybe I'm wearing a green and black shirt. Or
anything but a red shirt.
Yeah.
Red shirt
the red shirt. That's right. Klingon would come through that door and take me down, if I were in the red shirt. Things like that, right? Or more specifically, maybe instead of just the three of us, maybe there'd be another friend who was on here with us, or it would just be me and Stacy because Alan was out saving the world,
Oh yeah,
doing a
that,
secret
that would be an
mission.
exciting
You know,
universe.
yeah, that, that kind of thing. Can these things exist? Right? That's a multiverse concept. Now, is it true? Here's the thing: there are two physics slash math ways that we know of right now, based on the physics that we kind of think we know, where the multiverse could exist, something beyond just the physical universe, the three dimensions of space and one dimension of time in which we live. Okay, so these are two. There are many others, but these are the two that sort of are getting the most traction these days, as far as doing research in science is concerned. Okay, one has to do with the idea of inflation. Okay, this is not like you're paying much more for your blueberries in
Oh
the
man,
store
yeah.
than it used to be, right? But this is a concept that the universe, in its very, very early time, had this inflationary period where the universe expanded very rapidly, much faster than the current rate of expansion caused, uh, that we measure. We call the Hubble expansion, right? And so what happens here is that if inflation can happen in a universe, it can happen over and over again in different parts of the universe. And each inflationary bubble of the universe is like its own universe, right? It's so that would be an additional space-time chunk inside this very large other super space-time chunk. And so that
Yeah.
process is called eternal inflation. And within each of those bubbles is its own universe. So you can have a multitude of universes that coexist, but just cannot communicate with one another in any useful or meaningful way.
Yeah.
Right. The other kind of multiverse that's being commonly thought about has to do with quantum mechanics. Okay, in quantum physics, there is a mathematically equivalent way of thinking about how wave functions collapse and the coexistence of, say, Schrödinger's cat being both alive and dead at the same time, that kind of thing. And what happens is, in that interpretation of quantum physics, we call it many worlds interpretation, every time there is a possibility where a particle can either do this or do that, right? Decay or not decay, or vibrate or not vibrate, or whatever. Okay, in those cases, instead of one eventually happening and the other not happening, they both happen. And each time they both happen, a new universe is spawned. And so you have a
The universe
huge
just splits
number,
into these different.
yeah,
Yeah.
a multitude of split universes with every single event happening in the quantum universe, in the quantum realm, shall we say,
Oh boy.
um, going into creating its own new universe. Now, we are experiencing a common universe where all the things are happening in such a way that we all commonly experience. But there are many other universes that we don't experience that people similar to us may be experiencing, all because of this continuous splitting, separating, bifurcation of universes as quantum physics does its thing and the particles in the quantum universe do its thing and affect our macro universe as a result.
Yeah.
So either of those things could exist and possibly others. We just don't know. All right. Is there a multiverse theory that could be true or that has not been contradicted yet by the laws of physics that we understand now? The answer is yes. But do we know if they actually are there? We do not. So does that count as true or false? I don't know, Stacy. Uh, from your, you know, unclouded perspective, does that mean that universe theory is true or untrue?
It's got me scratching my head, but if there are multiverses, then I have two Piccolos at least. So
Even
Yes,
better.
right.
That's great.
One with metal fatigue and one without metal fatigue. Yeah.
there you go.
Yeah. No, I think yeah, it's very much just like a we don't know enough physics yet to be able to answer that
Okay.
definitively is where I'd sort of say it's like, a bunch it's like
Sounds
all
good.
these unknown questions. Riemann hypothesis or
Yeah.
something. We can't answer it yet.
Yeah. Okay. Question 3.
Right.
Okay, thank you, Michael. That was a good one.
Cool.
Yeah.
And this is one of the cool things about doing social media. I get to look at all the different places. So on Facebook here, we have Steve Bazinati. And Steve asks the following. And there are a couple questions in here, so I'm going to read it all as one thing. We all know that warp drive is still science fiction, But what is developing with other kinds of propulsion? Have we
Mm.
reached the limit of chemical propellants? And what is happening with ion drives and nuclear systems?
Well, we did have the Chang Diaz folks on telling us cool stuff at that point. But Alan, you're wired in.
Fair. Yeah, so the things going on with nuclear systems, ion drives, how we've reached the limit of chemical propellants, those are all really good questions in the rocketry area. I think we can definitely do a lot with chemical propellants still. I think in terms of like theoretically how much energy we're getting out of them versus the amount we could hypothetically get out of them, we're getting pretty close. So things like SpaceX's Raptor engine, which uses methane
Mm-hmm.
and liquid methane and liquid oxygen. Um, it's what's called a full flow stage combustion cycle engine, which is just a fancy way of saying it's like ridiculously powerful and very efficient using of its energy.
Wow.
And so we are getting close to the limit in that sense of like we're getting about as much energy out of these chemical reactions as the chemical reactions are giving off in the first place.
Cool.
That doesn't mean we
Cool.
can't just build bigger rockets and actually get more stuff into space with them. But in terms of other ways that are different than chemical propellants, there's a lot of really cool things out there. So you mentioned in this question both ion drives and nuclear systems. Ion drives, which basically is little particle accelerators to accelerate ions, these charged particles, outside of the back of the rocket engine at really high speeds, making them really efficient, but really, really low thrust, like 0 to 60 in
Mm.
days kind of thrust.
That would make the person trying to merge behind me really
It
mad.
really would, yeah. So yeah, there's definitely cool developments happening with those. I know that I think the Lucy mission is testing out an ion drive of some sort.
Mm-hmm.
Um,
Mm-hmm.
the Dawn mission to Ceres Invested did one in the past. As we mentioned earlier, we talked with the people working on the Vasimir engine, which is another electric propulsion idea that just
Mm-hmm.
uses electricity of some sort to heat a plasma and use that to drive the rocket. Basically, all these
Right.
are other energy sources other than chemical reactions we can use. Nuclear
Right.
propellants, in particular, when you're using a nuclear reaction to heat something up like hydrogen and use that as your rocket engine. I know NASA and I think DARPA are currently planning to launch one before the end of this decade in a very high orbit to keep it far away from the Earth so that the radioactive materials don't get anywhere near the planet. And they're hoping to actually test one out up there and see if they
No, that's
can
great.
get some really good rocketry out of that.
Perfect. Yeah, so I would encourage everybody who hasn't yet to go listen to that episode. In fact, the two-part episodes that you described, right? We
Yeah,
talked to
definitely do.
Dr. Franklin Chang Diaz and Miranda Chang about the cool stuff that they're doing with this Casimir system, which I think
Vasimir.
is really, excuse me, Vasimir system.
Yeah,
Yes. Casimir is a whole different thing. There's a Casimir effect, guys. You
yeah.
guys, we'll talk about that at some
That one's
future
a cool one, but that's an effect for a future time.
Yeah, cool. Okay, so Alan, do you have like a student question or something for us that we can answer?
Yeah, sure. We've got a question that goes back into the general relativity realm, sort of like we were talking about with the inflation. This is one
Okay,
was from Roberto J, and he is
okay.
asking, how was gravity created?
Whoa. How is gravity created is a great question, Roberto J. And unfortunately, we don't know the answer yet. There are some basic ideas. See, there's a period of time in the early universe. It's called the Planck time. It is the proposed period of time between the theoretical 0 point of time. Okay, if you interpolate or extrapolate time, it should end at a certain moment in the history of the universe where time equals 0. And then after that, expansion is happening and the Big Bang has occurred. But see, right at that very instant there, we call it the Planck time, 10 to the minus 43 second after the moment that the universe begins, if such a thing actually happens exactly as we think.
Yeah.
All right. That might be when gravity is created.
So
We
this
think
is
that at that moment, you've got all the forces in the universe all tied up into one. And then, boom, something happens in that very, very first instant, the tiny moment when all of our other physics is not yet well explained, where gravity appears.
this 0 time you're saying, is that just like if you extrapolate like the universe is currently expanding, and you just go backwards in time when it must have been smaller and smaller and denser. That zero time
Right.
is when it would have been like infinitely dense and infinitely small.
Yes,
And
that's
so
right.
we don't necessarily know if it happened exactly that way.
Yes, you're exactly right, Alan. We are not sure because it looks strange to think of the universe as once existing as a singularity,
Yeah.
right? Zero volume, infinite density. That feels weird. And in our fact, our laws of physics don't do very well explaining how that works. And so within that time, um, if something weird happens, that could be when things like gravity are generated, right? In fact, there's these terms called quantum gravity. They're trying to see how mathematically we might be able to predict the emergence of gravity as a force.
Yeah.
Gravity is not well explained by the rest of our ability to understand forces, the strong nuclear force, the weak nuclear force, electromagnetism, right? There's a particle called the graviton, which should exist and we think does exist, but we can't fit it well into this standard model particle physics. And, you know, it's just fun. There's lots that we still don't know, but that's kind of where gravity is likely to be created. And there's still so much uncertainty. There's a reasonable way of thinking about the Big Bang in the sense that the universe never really actually was that tiny. That internal inflation thing that we're referring to, what if the universe inflated first so there never was that extrapolation down to time of zero, but instead it only got down to like a millionth of a billionth of a trillionth of a, whatever second before that theoretical zero point in time. And then the Big Bang was the thing that came out as a result. Yeah,
That's pretty epic.
that's possible.
That's
It's epic. It's nuts, but it's possible.
yeah.
Yeah.
So whether the universe started at time zero or started at time millionth of a billionth of a trillionth of a second, it turns out to be this important physical question.
Yeah.
Even though that
Yeah.
sounds like the same amount of time. Zero and
Totally
barely
agree.
not zero, actually, it matters.
100% agree. Yeah. So great question, Roberto J. Thank you so much. Okay, Stacy, do we have another social media question from folks, not students, that just asked stuff?
We do. So our YouTubers are out there asking questions too. And somebody called Unexpected Books actually has a related question about gravity.
Hmm.
And the question is, how can gravity be transmitted via gravitons? It seems that a black hole would have no mass because gravitons, like everything else, couldn't escape it. Thanks for the answer. I love your channel. Thank you, Unexpected
Yeah,
Books.
thanks.
Yeah,
Yeah.
that is a very good question because indeed, black holes do have mass, right?
Yeah.
We know that because we are seeing the effects that black holes have on matter surrounding them, right? So we know that black holes do have mass. So do gravitons get sucked in? Excuse me. Remember, black holes don't suck. Do all gravitons fall in? Well, gravitons obviously, if they exist, as we mentioned in the previous question
Yeah.
from Roberto, that particular issue must mean that the gravitons are able to leave the event horizon of the black hole without actually having to be in the black hole,
Yeah.
right? And so that's good. But uh, do the gravitons actually exist? That's the question that we have. How can matter or mass know that there's this force called gravity if there isn't a graviton, right?
Yeah. So one thing I'm going to bring up that seems relevant is gravitational waves, right? So
Right.
we know from quantum physics that there's this wave particle duality, that waves and particles are sort of like two sides of the same coin here. And so we've
Mhm.
detected gravitational waves, which a lot of physicists say sort of means that there must be a graviton. It's not 100% certain, but there's several people who are arguing that sort of implies it. And
Mhm.
gravitational waves, we know, do come out of black holes. You know, we've seen black holes collide with each other. And those sort of, I think the best models that people are working on right now sort of see these gravitational waves as sort of radiating out from the event horizons of the black holes. So as those event horizons interact, as they get closer and closer to each other, and as these really strong gravity effects are warping space-time, that sort of sends these gravitational waves out into the universe. So if gravitational waves are as closely associated with gravitons as these people are suspecting, I imagine that it must be that the gravitons themselves would also be radiating out from the black hole's event horizons, sort of that surface of the black hole, like the last place that information can get away from a black hole before it falls in forever, or
I
for
like
mostly
that.
forever, depending on your theories.
Yeah, I like that. That's cool. Thank you. Appreciate that.
Yeah, that's the
Well,
thing that I can think of.
that's where I love that. No, that's where we are at this point, right? That cutting edge. It's a great question. Oh, thank you, Unexpected Books. Okay. All right. Alan, do we have another student question?
We do have another student question ready to go.
Okay.
This one is from Omar, and Omar is asking, does sound travel faster in space?
Oh,
This is an interesting one.
this is a great question, and I'm going to take a slight twist on not just what the question is saying, right? Because of course in space no one can hear you scream,
Right.
right?
That's
So
sort of the story.
supposedly out in space sound doesn't travel at all, right? But actually, it turns out that space out in the universe is not always pure straight vacuum.
Right. So
Right.
the reason that in
The-
space no one can hear you scream is because sound usually travels through something. So through
That's right.
matter. So either like water or air or something like that, where the atoms can bump or molecules can bump into each other and transmit that sound wave as those pressure of it bumping. And in space, there's almost nothing. So there's not really
That's
that
right.
much opportunities for the atoms to bump into each other. But you're saying that there's
That's
some
right.
sort of exceptions going on here?
Well, there's no exception to the physics rule that you described there. But out in the universe, what we call space, right? Say above 60 miles above Earth's atmosphere or whatever, or
Yeah.
above Earth's surface, there are plenty of places where there is stuff,
Okay.
right? So, for example, in surrounding regions around new stars, there's a lot of gas. It's much less dense than, say, Earth's atmosphere, but it's definitely there. There's media we call interstellar medium, or the intergalactic medium, or the intracluster medium. These are regions of space that have tiny amounts of particles per cubic meter or something.
So like 1 per cubic meter.
Yeah. And here on Earth, of course, the density is huge, right? It's a mole, Avogadro's number, right?
Yeah.
6 times 10 to the 23rd atoms or
60
molecules.
trillion.
Yeah,
Or
for just, a
1
little
trillion,
tiny bit.
trillion. Whatever.
Close enough. Right. So, in a box, say that's the size of a fish tank or something like that,
Yeah.
right? You would expect trillions upon trillions of particles so they can transfer sound through the water in the fish tank. But out in space, there's only a few particles. But sound could reach them and move through them. Okay. And the speed of sound, mathematical formula, not just sound here on Earth, but the speed of a sound wave, an acoustic wave traveling through a medium, has the mathematical formula has in its denominator the density of the medium. So if the density of the medium is very low compared to other things, or the change in pressure as a function of the change in density of a medium, can actually wind up creating a circumstance where the speed of sound through that medium is faster than even the speed of sound here on Earth.
Huh.
Okay. Just whether or not we could hear it is a different story, because the amount of energy being transported through that speed might be quite low, because the density of the material it's going through is so low that it's not pushing anything against our eardrums.
Okay.
So here's the difference between whether or not you can hear something and whether or not there's sound there at all.
Oh, that's philosophical now.
Yeah.
Wow.
And that differs from the pitch of the sound too. You can figure out that the wavelength of the sound, the frequency of the sound, those things are related, but you can wind up with very, very low notes traveling through the universe, because you have this medium in such a way with the energy flow going that is really, really low bass. And I just wanted to talk really, really low bass.
You're having a fun time with it.
Yes, but it does happen. It does happen out in space.
So there are sounds you just wouldn't be able to hear them because there's not enough particles involved.
That's right.
And they would
may,
potentially go really, really fast.
They could in fact be faster than the speed of sound here on Earth.
That's pretty
So
cool.
Wow.
Yeah, a more complicated question or more complicated answer than you thought when asking that question, I bet. Unless, of course, yeah, Omar was thinking about those fancy things,
Well, that would
and
be exciting.
in which case,
Well, it's
awesome.
just making me think about the whale songs, when the whales were
Oh
in Star
yeah,
Trek in
Oh
space.
yeah,
ooh,
yeah.
and
Save
then
the whales.
even on Finding Nemo too, where you speak whale by going very
And up and down
slowly
too. Yeah.
and up and down.
Awesome. All right.
I love that. Thank you so
Cool.
much, Omar. Great question. Okay, let's end on a Patreon question. Okay, does that sound like fun? Stacy, give us a
That
Patreon
sounds like
question.
fun.
Sounds
All
fun
right.
to me too.
Excellent. Okay. So we have Eric Shield here from Patreon. He
Eric,
says,
how's it going, Eric? I actually know Eric, everybody, but long story. We'll talk about it later. Please go ahead.
well, clearly you have a relationship because he starts the question by saying, "Hey, Professor."
Yeah.
I had a thought/question, but I'm not entirely sure how to properly articulate it, but I'm going to give it a shot. So here's what Eric asks. The Heisenberg uncertainty principle is a casuality of the particular mathematics we have used to explore the quantum world.
Ooh.
If we were to adjust those mathematics to a less consistent but more complete axiomatic viewpoint, could it be possible to see deeper?
Eric, how come I could have expected a question of this depth and interest from you?
This is fun
Anyway,
stuff.
well, thanks for asking that question. It's great. I'm going to take it from the physics point of view, but then I'm going to hand it off to our mathematician on this team, Alan,
Hey.
to talk about that mathematical thing.
All right.
Okay. The answer is for the physics part, we really do think that quantum physics sets a limit on the information that we can get at some low level, right? The Heisenberg uncertainty principle has been shown to be true over and over again, which means that if you know, for example, the energy of a system very, very precisely, if you can measure it really well, um, then that's great. But the time resolution of that measurement would be very bad. So this kind of exchange as loss of information is indeed a mathematical thing, but it's a physical thing as well. Now we're trying to overcome that by string theory, for example, which you're trying to think of deeper dimensions, but within each dimension, there's still that uncertainty at the moment within our sort of three dimensions of space and one dimension of time determined by Heisenberg uncertainty principle. Eh, who knows,
Yeah.
right? The higher order math, especially the string theory side of things, I leave to Alan to give us a little bit of insight.
Yeah, sure. So there was a really cool explanation that I saw about a mathematical end of the uncertainty principle, which is if you're looking at so you know how like when you have an audio editing software, I look at the audio editing software every so often, you'll see like how loud your sound is at different frequencies. So you'll have like a little picture, a
Mhm.
little graph that'll have like a 2D graph where it's like what time it is and how loud at each frequency, at each pitch you're being at any given time.
Yeah.
It turns out like sort of if you look at a very small window of time, um, you can get a very good sense of what the sound level is at that particular moment in time, but
Hmm.
you can't get a good sense of how that frequency breakdown is because the low frequencies have such a long time between them. So something like 10 hertz vibrates 10 times a second. That's like a frequency that I think we can hear. It's sort of toward the low end of things we can hear.
Hmm.
You might, if you're looking at a period of time that is less than 1/10 of a second, you can't see frequencies that are 10 hertz because 10 hertz vibrates at 10 times a second.
Hmm.
So it's sort of it's a question of how small of a window or how big of a window you can look at, whether you can see those frequency resolution better or that time resolution better. So you can't exactly get both perfectly at the same time, but what you can do is
Okay.
change the trade-off between them. So
Ah.
you can, if you see something like a Fourier transform, which is a mathematical way of breaking a sound down into its frequencies, that is very good at frequency resolution, but it's very bad at time resolution. And if you on the other hand see something like a waveform, you can see something that's very good at time resolution, but very bad at frequency resolution.
Mm. Hmm.
But you
Hmm.
can get something sort of in between. So something like a wavelet transform is an example. So you can sort of
Ah.
say, well, I care about some about frequency and some about time, and 4 different sounds in the system, I can make it that one of them cares more about frequency, one of them cares more about time, one of them is sort of in between. And you can get a good picture of the entire data, sound data or weather data or any other sort of thing that oscillates up and down by changing how you're using that trade-off on different parts of the data. See, this trade-off, you can't entirely get rid of it. You can't entirely get away from it. And I could talk about this whole consistent but complete issue with Gödel's and completeness theorems as well, but I'm not going to do that right now because that doesn't seem.
Oh, but do that
part of the
someday,
question.
okay? All right.
I will do it
Make
at some
sure to
point in
do
the
it
quiz.
someday.
Yeah,
I would.
that's a fun philosophical and mathematical discussion as well. But in terms of actually
Yeah.
getting data and being able to see deeper, yeah, things like that you can use the trade-off in a different way that gives you the information you would like to see, even though you can't fully get away from having to have that trade-off. You can sort of work within it.
Marvelous. That's a great way to end. Thank you, Eric, for this great question. Thank you to all of our Patreons. Look, ask those questions, and those of you on social media, Facebook, everything. This was so much fun.
It's great.
Obviously, we're going to do this again sometime. Well, maybe we'll turn this into a thing because,
We've done a couple now.
ChatGPT is now at 4, right?
4.0 even. Not even just a
Oh
number.
my
They have a letter
goodness.
on it now. It's 4.0.
Wow. Okay, we'd better get to it sooner rather than later. Well, this has been so much fun. Stacy, thank you so much for gathering these questions for us, helping us out, and just doing awesome stuff for the LIUniverse.
Thank you for having me.
Oh, it's a real pleasure. And as always, co-host Alan Liu, thank you so much for everything. And
Yeah.
great questions and great answers. Thank you.
Yeah, you're welcome. Glad to be here as always.
And to all of you in our audience, we're really, really glad that you could join us today for this episode. Thank you. If you like what you see and hear, please support us on Patreon. And as always, thank you for being a part of the LIUniverse.